In roughly 1 billion years, the oceans will start to evaporate, and they will not stop. Not because of climate change, not because of anything humans do or do not do, because the sun is getting hotter, has always been getting hotter, and in 1 billion years, it will be hot enough that the water cycle on Earth breaks in a direction it cannot recover from. The oceans go into the atmosphere loses them to space, and the planet that was 70% water becomes something that looks a lot like Mars looks right now. Bare rock, dry, silent, baking under a star that is slowly killing it. This is not a theory. It is not a worst-case scenario. It is the most thoroughly understood and well-supported prediction in all of astrophysics, worked out from the same physics that explains why the sun rises every morning and why it is warm when it does. The sun is a star. Stars age. Aging stars get hotter. Ours is no different, and never was. Here is where we are right now. The sun is about 4.5 billion years old, roughly halfway through its hydrogen-burning life. Right now, at this moment, it is about 30% brighter than it was when the first simple life appeared in Earth's oceans. 30% sounds like a lot, but it happened so slowly, over such an enormous stretch of time, that life adapted continuously and never noticed. The planet adjusted. The atmosphere adjusted. Everything calibrated itself to the slowly increasing heat, without any single generation of anything ever experiencing a meaningful change. That will not always be possible. The sun adds roughly 1% more brightness every 100 million years. At current rates, in about 600 million years, the increased solar radiation will push Earth past a threshold where the chemistry of photosynthesis stops working efficiently for most plant life. Not all plants, not immediately, but the cascading effects on the food chains that depend on photosynthesis will be significant. The planet that exists in 600 million years will be dramatically different from the one that exists now, even before the ocean evaporation begins. How do scientists know any of this? Not from guessing, from watching other stars. The galaxy contains hundreds of billions of stars, and a significant portion of them are sun-like. Similar mass, similar composition, similar age range. Some of them are younger than the sun, some older. And by studying stars at different stages of the same process, astronomers have built a picture of what happens at each stage, the way a doctor builds a picture of how a disease progresses by studying patients at different points in its course. When you look at a star slightly older and slightly more evolved than the sun, you are looking at the sun's future. The physics does not change, the chemistry does not change, the timeline shifts, but the story is always the same. The other thing scientists use is Mars. Mars is smaller than Earth and farther from the sun, and it has no magnetic field to speak of, which means solar wind has been stripping its atmosphere away for billions of years. What Mars is now? A dry, cold, thin atmosphered rock with traces of what were once river valleys and lake beds, is a rough preview of what Earth becomes when its water leaves. The Curiosity and Perseverance rovers have spent years driving across what was once a wet planet, photographing ancient riverbeds and lake sediments and the chemical traces of an environment that could have supported life. Mars did not lose its water because of the sun specifically. Its own small size and lack of magnetic field were the primary causes. But it shows in uncomfortable detail what a world looks like after the water is gone. Earth's fate looks different in the details, but arrives at a similar place. Then comes the billion-year mark. The oceans start going. The process takes time, hundreds of millions of years, but once it starts, it accelerates, and it does not reverse. As water leaves the surface, it enters the atmosphere, and as it enters the upper atmosphere, it gets broken apart by solar radiation into hydrogen and oxygen, and the hydrogen, being light, escapes into space. Gone. Not stored somewhere. Gone. The water that was an ocean is now scattered atoms drifting away from the planet that used to hold them. Earth's water budget has been decreasing slowly for its entire history, and in a billion years, the rate of loss overtakes the rate of any possible replacement. 2 billion years from now, the surface of Earth is somewhere between uninhabitable and actively hostile to anything we would recognize as life. The temperatures are extreme. The atmosphere is thick with carbon dioxide and water vapor in whatever quantities remain. If anything is still alive, it is microbial, deep underground, nowhere near the surface. The planet is not dead in an absolute sense. Some chemistry is still happening somewhere. But the window for complex life closed long ago. None of this is the main event. All of this is the buildup. Around 5 billion years from now, the sun runs out of hydrogen in its core. Not runs low, runs out. The nuclear fusion that has been keeping the core hot and pressurized for 10 billion years stops. And the core, no longer supported against its own gravity, begins to collapse. As it collapses, it heats up. The temperature in the collapsing core rises to the point where helium, the ash left over from hydrogen burning, starts fusing instead. And the energy released by this new fusion process pushes outward into the sun's outer layers with more force than anything the sun has ever produced before. The outer layers expand. This is the understatement of the next 5 billion years. The sun's diameter grows from its current size, about 100 times the diameter of Earth, to somewhere between 100 and 200 times its current size. The surface cools as it expands, going from the yellow-white of the current sun to a deep red, which is why this phase is called a red giant. The sun becomes a red giant, and a red giant the size of what our sun will become puts its outer boundary somewhere around the current orbit of Earth. Mercury is the first to go. Its orbit decays as the expanding sun's gravity and radiation work on it, and it spirals inward and vaporizes. Not crashes, not collides. Vaporizes, turn to gas, its atoms absorbed into the outer layers of the expanding star. Venus follows the same path. Whether Earth survives technically depends on the math of how much mass the sun loses during expansion, and how that changes Earth's orbital distance. Some models say Earth drifts outward just enough to avoid being engulfed. Some say it goes the way of Mercury and Venus. Every model agrees that whatever the answer is, it does not matter in any practical sense because the surface of Earth by this point is at temperatures measured in thousands of degrees and has been uninhabitable for billions of years already. Mars is an interesting case. Mars is currently too cold and too thin atmosphered to support liquid water on its surface. As the sun expands and brightens during the red giant approach, Mars warms. The polar ice caps melt. The thin atmosphere thickens slightly as frozen carbon dioxide sublimates. For a period, geologically brief but astronomically significant, Mars might have liquid water on its surface again, for the first time in billions of years. Whether anything could live in that briefly warmer Mars is an open question. The conditions would be extreme by any measure. But for a window of perhaps tens of millions of years, the planet that was once wet and is now dry would be wet again, one last time, before the expanding sun gets close enough to boil it off for good. What happens in the outer solar system during the red giant phase is genuinely strange. The regions that are currently frozen solid, the ice moons of Jupiter and Saturn, the frozen world of Titan with its methane lakes, the distant icy objects beyond Neptune, all of these receive dramatically more energy as the sun expands and brightens. Europa, currently locked under kilometers of ice with a liquid ocean beneath, kept warm by tidal forces, would have that ice melt entirely. The ocean that has existed in the dark under that ice for billions of years would be exposed to sunlight for the first time. Enceladus, which already shoots geysers of water into space through cracks in its ice shell, would open up completely. Titan's thick orange atmosphere and surface chemistry, currently one of the most complex environments in the solar system outside of Earth, would go through changes that are difficult to model, but involve dramatic chemistry driven by a completely new energy budget. There is a window. It lasts somewhere between a few 100 million years and maybe a billion, depending on which models you trust. During this window, some of the outer moons of the giant planets are warm enough to have liquid water on or near their surfaces. They receive enough energy for complex chemistry. The moons of Jupiter and Saturn become, briefly, the most potentially habitable places in the solar system. If anything survives from Earth's biosphere long enough and has the capability to move between worlds, this is where it goes. It is a strange kind of hope. Everything you currently know is gone. The inner solar system is a furnace. But out past Jupiter, there is a temporary warmth that did not exist before and will not last long after. The red giant phase does not last forever either. After the helium in the core burns out, the sun loses its grip on its own outer layers. The gas drifts outward into space in an expanding shell. Astronomers call this a planetary nebula. A terrible name because it has nothing to do with planets. It is a historical accident of naming. What it actually is a sphere of glowing gas surrounding what is left of the star, lit from inside by the radiation coming off the core. Some of the most photographed objects in astronomy are planetary nebulae, the Helix Nebula, the Ring Nebula, the Cat's Eye Nebula. They are genuinely beautiful, luminous shells of gas in extraordinary colors, caused by the different elements glowing at different wavelengths. Every one of them is the death shroud of a star like the sun. Every one of them was once a solar system. What is left of the core after the gas escapes is a white dwarf. A white dwarf is the exposed heart of a dead star. The sun's white dwarf will be roughly the size of Earth. Not because Earth is the right size for a white dwarf, but because that is how the physics of electron pressure and gravity work out for a star of the sun's mass. It will contain about half the current mass of the sun compressed into that volume. The density is almost impossible to picture. A teaspoon of white dwarf material weighs about 5 tons. It will be white hot initially, glowing from the residual heat of everything that came before, and it will cool over trillions of years, going from white to yellow to orange to red to something that emits no visible light at all. Astronomers call that final stage a black dwarf. No black dwarfs exist yet in the observable universe because cooling a white dwarf all the way down takes longer than the universe has currently existed. Every white dwarf currently known is still warm enough to glow. The sun's eventual black dwarf phase is so far in the future that it sits beyond any human concept of time. A cold, dark object drifting through space where a star used to be, in a solar system that will still exist in some form, with whatever planet survived still orbiting something that no longer provides them anything. Jupiter will still be there. Saturn will still be there. Its rings probably disrupted and changed by everything that happened during the red giant phase, but the planet itself surviving. The outer planets are far enough from the action that they make it through, cold and dark, orbiting a white dwarf that gives them a fraction of the energy the sun currently provides. The moons that were briefly warm during the red giant phase will be frozen again, colder than they are now. The solar system will be quiet and dark with an ember at its center and ice and gas and rock moving around it in the silence. As for humanity, or whatever comes after humanity, or whatever intelligent life exists in this solar system a billion years from now, the question of what happens to it is the only part of this story that is genuinely open. The physics of what the sun will do is settled. The physics of what civilizations can accomplish over geological timescales is not. A billion years is an almost incomprehensible amount of time. Modern humans have existed for roughly 300,000 years. In a billion years, there could be civilizations that have had 1,000 times the history of everything that has happened on Earth so far. What they could build, what they could move, what they could reach, is genuinely unknowable. Moving a planet's orbit is not physically impossible. It requires enormous energy and engineering on a scale that does not exist now, but nothing in the laws of physics forbids it. Reaching other star systems is not physically impossible. It requires propulsion and time scales that are not currently achievable, but nothing in physics says they never will be. The window is 1 billion years. That is the time between now and when the oceans start going. Whether anything that begins in this solar system uses that window is a question nobody alive today will ever know the answer to. The sun right now is burning through 600 million tons of hydrogen every second. Every second. The fuel supply is enormous. It has lasted 4.5 billion years already and will last another 5 billion. But it is finite in a way that has consequences that are not abstract. In 1 billion years, the oceans start going. In 5 billion, the sun swells to engulf the inner planets. In 10 billion, there is a white dwarf where the sun was, and the solar system is cold, and the thing that made all of this possible is gone. Tomorrow it will rise in the east the same way it did today. It will cross the sky. It will set. It has done this for 4.5 billion years, and it will keep doing it through every human life that will ever be lived, through whatever comes after human lives, for longer than anything currently alive can meaningfully imagine. But the hydrogen is finite, and every second that passes, there is a little less of it.